Okay, go through these. Now, partially out of laziness, but also motivation for you, these are questions taken directly from the homework. So if you've been doing your book problems, you should have looked familiar. I didn't change the wording or anything. Okay, so the first one, simple, good old gas law type problem. Mass is 0.555 grams. You've got volume, you've got temperature, you've got pressure, and it wants you to find the molar mass of the gas. So in this one, if you didn't, you just have to know PV equals nRT, and you know that moles equals mass in grams divided by molar mass, right? Is that right? Yeah. All right, and let's go outside. Okay, let's finish talking about this quiz quickly, and then we'll get into other stuff today. If we don't finish stuff up today, we'll have time on Monday, because that lab doesn't take very long. So. Okay. Oh yeah, so we set up the equations before we all caught on fire, and then let's just fill it in, right? So pressure, 753 millimeters of mercury. We have to convert that. So it ends up being 0.99. So that's our pressure. Volume is 0.117 liters equals the mass, 0.555 grams, divided by the molecular weight, times R times T, which is 273 plus 85, or 358 K. Okay? Solve for M. Something like 141 grams per mole.
You can get there other ways, right?
You can get there other ways. Yeah, you could solve for moles and then figure it out from there. Yeah.
It's actually 140.
140? Oh, 85 degrees C. Yeah. Okay.
141 is what?
I think I know. Just around there.
Around there is fine, we'll say. Okay, fine. Okay, and then this one also from the book. You had to look at the equation here, which was sodium azide decomposes into sodium metal and nitrogen gas. Okay? Is this balanced? No, it's not. So we've got to go 3 of these, 2 of these, 2 of these. Okay. Yeah, maybe. If an automobile airbag has a volume of 11.8 liters, what mass is required to fully inflate the airbag upon impact? So the point being here, you need to know how many moles of N2 can occupy 11.8 liters at STP. All right? So that's 11.8 liters times 1 mole, 22.4 liters. .527 moles. Okay, so that's the amount, that's the moles of N2 that you need. Okay. So now we figure out the moles of sodium azide that we need to make that many moles of N2. So we'll take the 0.527 moles of N2 times the molar ratio, which is 2 moles of sodium azide divided by 3 moles N2. And that gets us 0.351 moles. Okay? And then 0.351 moles of sodium azide times the molecular mass of sodium azide. So sodium is 23 plus 28 for the 2 is 51.
Wait, it's in 3.
Oh, it's in 3, yeah, sorry. So it's 51 plus another 14, so 65 grams per 1 mole.
Roughly
22.8. Okay, so that's how many grams of sodium azide you need. When I wrote this question in, I was considering not telling you what the formula for sodium azide, but I ended up putting it in there. So know that azide is an ion that you should know for the future. N3 minus. Okay, and then this final one, this was straight from the book, except that I gave you some values instead of, I think the book just says equimolar amounts. Flask at room temperature holds exactly that many molecules, so about half a mole of nitrogen gas and about half a mole of xenon. Which of the two gases has the higher partial pressure?
is the same.
It's the same. Why?
Goes in the formula PV is equal to 1 just divide pretty much everything that's, because it says it is the same temperature, it's the same amount of moles,
Right.
and it's the same volume.
Right. So partial pressure is proportional to mole fraction. If it has the same number of moles, then it's the same partial pressure. Okay. Remember, partial pressure equals mole fraction times total pressure. So, yeah, tracks with moles. All right. What about the greater average velocity? Nitrogen. It's the lighter gas. N2 is 28. Xenon is 131. So it's a lighter gas. So it'll be moving faster at the same temperature. And what about the greater average kinetic energy? Same. They're at the same temperature, so they have the same average kinetic energy. One is heavier, so it's moving slower. One is lighter, so it's moving faster. But the temperature is proportional to the average kinetic energy. All right? Questions? Okay. This kind of stuff will be, well, all of this stuff will be a big part of the exam a week from Monday. A week from Monday or 2 weeks from Monday? A week from Monday, yeah. So please work on these Chapter 5 problems. The stuff that wasn't on the quiz today, just because quiz is short, stuff about partial pressures, mole fractions, all those problems, we did some on Monday, but make sure you're somewhat comfortable with those as well. So some of this you've probably heard already, but all of this really comes into these two definitions. All right, the energy is defined as the capacity to do work or produce heat. So you can transfer energy by doing work on something, meaning I lift this up, I do work on it, okay? Or I can transfer it in heat. I can transfer heat from me to something else, then I've transferred energy to something else. And in chemistry standpoint, we have this, well, from an everything standpoint, we have this law of conservation of energy. So energy can only be converted from one form to another. So you can take heat energy and turn it into work energy, or work energy and turn it into heat energy. You can transfer it from one place to another, but you can't create it or destroy it. Okay? The energy of the universe is constant, at least in chemical reactions. Potential energy we'll define as the energy due to position or composition. So either where it is, as in a ball that's very high has potential energy because it can fall, or composition, something made of a high energy substance can undergo a reaction and then lose that energy. And then kinetic energy is energy due to the motion of a body. And if you've taken physics, you've probably heard a lot of these kinds of things before. So kinetic energy is the energy of motion. All right, and then we'll talk about heat versus temperature. We've talked about a temperature already that has to do with, well, we've talked about it in terms of gases, but in all substances you can kind of imagine where that's going. It's the motion of the particles. It reflects the motion. So it has to do with the kinetic energy in many cases of particles, but something about the motions of particles. Heat refers specifically to the transfer of energy due to a temperature difference. So heat and temperature are often used interchangeably in everyday life, but in scientific terms, heat is talking about transferring energy due to a hot thing and a cold thing. Okay, and the energy transferring, that energy is known as heat. The temperature is what you think of as a temperature, the thing you measure that is proportional to the kinetic energy and so forth. And then work is force acting over a distance, so taking something from one place and putting it somewhere else. And you can transfer energy in two ways. What are those two ways? We just said them. Heat and work. So you can transfer energy in two ways. You can transfer heat, right? You can do work. That's it. And then we're going to talk about something called a state function. Energy or temperature change is independent of how that change occurs. Meaning, if you're at one energy and then you're at another energy, okay, the delta E doesn't matter how that change occurred. It just matters that there is a change. Whereas work and heat are actually dependent on how that change occurs. And I'm going to give you some examples of what that means. So energy is what we call a state function. And that system only depends on its present state, not how it's changing. All right. Here's the picture from your book. That's kind of a good example. Altitude is a nice way to picture a state function. Your altitude doesn't matter how you got there. Your altitude could change from a very direct path, or your altitude could change from a very circuitous path. Distance traveled is different, but the altitude change doesn't depend on the path that you take. So altitude is a state function like energy, but distance traveled would be not a state function like heat or work, where it actually depends on how you get there. So in a chemical example, we can talk about what a chemical reaction does to the system or the surroundings, how it transfers its energy, and how it changes energy state. So we have two parts of a chemical reaction. I mean, lots of parts, but we talk about the system and we talk about the surroundings. The system in chemistry is the reaction. The surroundings is everything else in the universe. The more general term is whatever you're focusing your measurement on is the system, and everything else is the surroundings. So for a chemical reaction, the system is the collection of reactants and products. What specifically are the surroundings in a chemical reaction? Rather than just everything else, but I mean, what are the more direct surroundings that you might think of in a chemical reaction? The solution. So, like, if water is not participating in the reaction, but the reaction is being done in water, then that extra water is part of the surroundings. Spectator ions can be part of the surroundings. Glassware is certainly part of the surroundings. The air around the reaction is part of the surroundings. And then, of course, you could go on and on outward to the whole room. And we've probably heard these words before. Exothermic reaction gives off heat. So energy flows. Well, okay, let's talk about this a little bit more specifically. An exothermic reaction, we say it gives off heat. It gets hot. If you burn something, that's an exothermic reaction. It's giving off heat. But in the terms that we just talked about, in terms of energy, heat, and work, how we might say this is an exothermic reaction transfers energy from the system to the surroundings by means of heat. So it takes its potential energy and transfers it as heat to the surrounding. And then an endothermic reaction does just the opposite. It takes in energy from the surroundings as heat. And because of the law of conservation of energy, whatever energy is lost by the system is gained by the surrounding. So when something gets hot and it transfers that energy to the, when something's exothermic and then it cools down, it doesn't mean that it lost that energy. It means that that energy was all transferred to the surroundings and it's now all in the air. So we never talk about energy being lost from everywhere. That would be impossible. We just talk about it being lost from the system, being transferred to the surroundings. So here's combustion of methane. You've got potential energy due to the composition of the molecules, the CH4. And that energy is converted to the thermal energy via heat. So the energy is lost from the system to the surroundings. And this is kind of a big deal these days when we talk about energy usage and alternative energies and things like that. The reason this stuff works so well is that fossil fuels, methane, coal, gas, whatever, have a lot of potential energy. A lot of potential energy, especially a lot for how light they are. So they make for very, very, very good fuels. And that's why it's so difficult to come up with alternatives to these things, because they just hold so much energy within them. All right, and that's pretty much all we're going to talk about. Now, I do want to show you what a couple problems might look like that deal with these energy things. Here's some problems that I might ask you and that you'll see in this chapter 6, Max Strength Chemistry. So identify this as heat or work and determine whether it would be negative or positive. The heat or work is negative or positive. An ice cube melts and cools the surrounding beverage. If the ice cube is the system, what's the surroundings? The beverage, right? So what's happening now? Is heat or work being done? Heat. Right? And is the heat change positive or negative? Why?
It is given to the plastic to melt it.
That's right. Heat is transferring from the surroundings, the liquid, to the ice cube to melt it. So even though the English is confusing because it says the ice cube melts, it's actually the surroundings that are transferring heat to the ice cube, because you can't transfer heat from a cold thing to a hot thing. So the ice cube melts and cools the surrounding beverage. That means that there is a heat change. The energy change is due to heat, and it will be positive because the system will gain in energy relative to the surroundings. Okay, next one. A metal cylinder is rolled up a ramp. That's work, right? And is the work positive? Is the work done on the system? Or is the work negative? The work is transferred from the system to the surroundings. How many people say positive? How many people say negative? Okay. In this case, let's think about what's happening to the metal cylinder. Does it have more potential energy at the bottom of the ramp or at the top of the ramp? At the top. So it's gained in energy, right? And it's gained that through work. So that means that the sign is positive. Right? The cylinder has gained energy as you push it up the ramp. You've transferred energy from yourself to the cylinder by doing work and pushing it up the ramp. And then finally, steam condenses on skin, causing a burn. This one's a little bit tricky. Oh wait, the answers are right there. Did anybody see that? Okay. Well, don't look at it. I didn't even see that. Of course, everybody's looked at it now. Steam condenses on the skin, causing a burn. So what's happening there? It's a transfer of heat, right? Work isn't being done here, it's heat. which way is the heat going? Is the heat going from the steam to the skin or from the skin to the steam? Positive. So it's transferring to the steam. Yeah.
But first of all, we have to name which one's the system, which one's the.
It says here. Yeah. So the condensing steam's the system. So let's talk about why that couldn't be the case. If you're saying that the steam is the system, and therefore it is positive, that means it's taking heat from the skin to the system, to the steam, right? That wouldn't cause a burn.
No.
You need to be putting heat into the skin to cause a burn. And so that would be negative. Negative heat.
But one more example of like alcohol, like the alcohol on your skin when it cools.
Yeah, so alcohol on your skin feels cold, right? Because what's happening when you put alcohol on your skin? It evaporates. And it takes heat to evaporate something. So the alcohol is pulling the heat out of your skin, using it to become vapor, and then your skin feels cold. All right, so let's keep with that example. If you are the system, and you not the alcohol, but if you are the system and you put alcohol on your skin, is the heat negative or positive? Negative, because the heat is going away from you into the system, which is the alcohol, or into the surroundings, which is the. So that's the sort of thing that I want you to be able to think about with these. Nothing fancy, just those basic ideas about energy. Yeah. Mm-hmm. Because you have to, because the answer changes. Yeah, because depending on which one you define as the system or the surroundings, the sign is opposite. So you have, yeah. But that's actually an important point with this stuff, is we always have to define the system. We have to know what we're measuring, what we're looking at, so that we can get those signs correct. Okay, ready for some quantum mechanics? Everybody just looked at me like you wanted to punch me. Yeah. So that was it for chapter 6. On to chapter 7. Okay, this chapter, there's a few math things that we want to talk about, but also a lot of interesting kind of theory and descriptive stuff that we'll build into, especially in chapter 8 and 9. So first, we need to talk about electromagnetic radiation. What's electromagnetic radiation? In your own words, not in those words necessarily. What do you think of as electromagnetic radiation?
When electromagnet sends off waves.
Okay, when an electromagnet sends off waves. Okay. Those are actually mostly just magnetic waves, but yeah. What's another way to say electromagnetic radiation? In a simpler word. Light. Right? This is light. Now, light is a little bit misleading because a lot of electromagnetic radiation is light you can't see. Radio waves, microwaves, all that, X-rays. Those are all forms of electromagnetic radiation. But actually, all of these are types of light, just with different properties, with different wavelengths and different frequencies. So if you have some math behind you, I'm sure you've heard these words before. Wavelength, if I draw a wave, wavelength is the length of the wave, right? The distance between two consecutive peaks or troughs, or one full cycle of a wave is one full period. The length of one full period is kind of the more official math definition. But if we just look at like these 2 points, this is the wavelength lambda. So a larger wavelength is a wave that oscillates more slowly, right, or over greater distance. And a short wavelength is a wave that goes like this. Frequency, then, is the number of cycles per second. Okay. So as the light or as the wave, the electromagnetic radiation propagates in space, how many cycles do you have per second? Do you need to know the speed of the wave for this to be true? Or for this to make sense?
Yes.
Yeah, but for light, we know that, right? Because we know, I mean, maybe we don't know it offhand, but we can look it up. All light travels at the same speed, the speed of light. So as light is traveling, the frequency is the number of cycles per second that pass a given point. And note that this symbol for frequency, what is that? It's not actually, which is always why it's confusing. It's not a V. Anybody know what it is? It's nu. It's nu. Nu. It's a Greek letter. Okay. So try to make it different from your V's. I know it's hard. It looks like a V, but it is nu.
Can we just say like F, cursive F, for frequency?
No.
It's the same thing.
Where is cursive F frequency?
I mean, that's what I signed for this class.
Really?
Yeah.
I thought cursive F is usually... Cursive F is tricky because it often refers to a function. So nu is the more traditional one. Sorry. So we can actually show a relationship between frequency and wavelength using speed, right? Because we know that speed it relates these two together. So wavelength times frequency equals speed. Wavelength is in meters. Frequency is in inverse seconds, or 1 over second. So if you multiply those together, you get meters per second, which is speed. If you've heard this unit hertz, that's also cycles per second, 1 over second. All right, so here's a picture of the electromagnetic spectrum and all of the different types of electromagnetic radiation. You've got the very low energy stuff on the left. That's stuff with very big wavelengths and very low frequencies. I mean, relatively. So that's things like radio waves, which have huge wavelengths. You know, wavelengths on the order of kilometers, miles. Then you've got microwaves, which are what most cell phones run on to communicate with the cell phone towers, as well as, of course, the microwave oven. You have infrared light, which is what we see mostly transferred as heat. So it's irradiative heat transfer sometimes through infrared light. And then you have this tiny little portion, which is the visible light spectrum, going from red at about 750 nanometers wavelength to violet at about 400 nanometers wavelength. So we'll often be talking about light in the nanometer region because that's the visible light, is all with wavelengths in the nanometers. Remember that a nanometer equals 10 to the 9th meters. Then higher energy rays, you've got the ultraviolet, the X-rays, gamma rays from space. So let's try a couple problems. You should be able to do these types of conversions. Brilliant red colors in fireworks due to emission of light with wavelengths around 650 when strontium salts are heated. Calculate the frequency of red light of wavelength 650 nanometers. So use that equation above, see if you can get that, and then we'll do it together. This one is, remember, same equation. C equals nu times lambda. So that equals the frequency which we're trying to find times the wavelength in meters. Okay. Wavelength in meters is 6.5 times 10 to the 7th. Yeah, because it's 650 nanometers. So that's 6.50 times 10 to the 7th.
Would it be negative?
Yes, thanks. 10 to the minus 7 meters. All right, so C is 3.00 times 10 to the 8th meters. Okay. It's about, what, 300 million right? Meters per second. So you divide those two. Whoops. You should get about frequency equals 4.62 times 10 to the 14th inverse seconds or hertz. If you go back up to this, that should fit approximately right. 650 nanometers in the red. Whoops. Is on that order of 10 to the 4th. The entire visible spectrum is basically around 10 to the 15th hertz in frequency. Okay. All right. So you should be able to do that sort of thing. Now we're going to talk about the energy of these things. And this is where we start getting into the sort of the controversial things that are not really controversial anymore, but certainly were at the time. Because we thought that there was this very clear separation between matter and energy. Matter did matter things, energy did energy things, and there were no shared properties there. Right? Energy was a wave, matter was a particle. Okay, done. And the very beginning of quantum mechanics is Max Planck discovering that matter only gains energy in whole number multiples of the frequency times a certain constant. He called that h nu. Right. So what that means is that matter only gains energy in these little packets. The change in energy of anything must be n, some integer, times h, which was this constant that he found, Planck's constant, times nu, the frequency of that energy. That doesn't seem totally crazy, but it did at the time. Because if energy is this massless wave thing, then you should be able to put as much or as little energy into something as you want. It should be completely continuous. You can put, an infinitely small amount of energy into something, all the way up to a large amount of energy in a perfectly continuous range. But what he found is, in fact, that's not true. The energy goes in these little packets, kind of step by step. Now, they're very, very tiny packets, right? 10 to the minus 34 times the frequency, so you end up with something a little bigger than that, but still a small packet. But it's still packets, and he called those packets quanta, and that's where we get quantum mechanics or quantum physics. The energy can only be transferred in little packets. And the reason that's so important is that energy is no longer continuous. Energy can actually be boiled down to a particle with an actual amount of energy. Now, that particle doesn't have mass, but that particle certainly has energy. So, and we'll talk about kind of the mass part of that in a little bit. So we can actually look at the individual energies of these little packets that are emitted by certain processes. All right, so the blue color in fireworks, you've got copper chloride at 1200 degrees C. And then it starts emitting a blue light with a wavelength of 450 nanometers. What is the increment of energy, the quantum, that is emitted at 4.5 times 10 to the 2 nanometers by copper chloride? So to do this, we can actually set up this equation. No, you don't have to remember that constant. There's your equation, E equals h nu. And remember from before that c, speed of light, equals lambda times nu. So we can rewrite this as E equals hc over lambda, because rearranging this equation gives us nu equals c over lambda. So that means that we can multiply this constant, 6.626 times 10 to the minus, what did I say it was, 34? Yeah. 34 joule seconds times the speed of light, 3.00 times 10 to the 8th meters. And then divide that by the wavelength, or that's meters per second, sorry, meters per second. Divided by the wavelength, which is, in this case, 450 nanometers, or 4.50 times 10 to the 7th meters. What? Yeah, negative 7. At least I get, which may be wrong. 4.42 times 10 to the negative 19th joules. So that means 450 nanometer light can only transfer energy to things in these little packets of that many joules of energy. So a tiny amount of energy, to be sure, but still a quantized amount of energy. And that means that we can actually define this little particle as something called a photon. And so this is what a photon is. It's a massless particle that has a particular wavelength and transfers energy in a packet with a certain amount. Okay, so Einstein actually discovered this before all the nuclear stuff that he worked on that we probably know him better for today. But this was really his big thing. He hooked up a power source to something called a photoelectron tube, or a photoelectric device. And what happens is when you give it just enough power, an electron, or I'm sorry, when light hits it, an electron moves. Electron moves from this metal plate to the positive terminal, and you can measure that current. Okay. And so what he found was that, in fact, any metal would do this at different energies of light. And so you can actually measure the energy of this, or you can measure the energy of the photon based on the current that it produces. And so the big take-home of all of this is that electromagnetic radiation is not just a wave. It actually is both a wave and a particle. So it behaves like a wave and behaves like a particle. So this is known as the particle-wave duality, or the dual nature of light. And then this was extended further to say, well, okay, if light can act like a particle by transferring energy only in little photons and little packets, can matter also act like a wave? And the answer is, yeah. You can rearrange the equations to talk about how you can actually say that a wavelength can be, or a particle of a given mass can have a particular wavelength, or mass and velocity can have a particular wavelength. Note that this is v now, not nu. Need a little extra room here. Sorry. So let's take a look at this question. The wavelength for an electron traveling at a speed of 1 times 10 to the 7th meters per second, for that with a ball, a 100-gram ball, traveling at 35 meters per second, or a fast pitch, right? Very fast baseball pitch. So let's look at those wavelengths. Remember the equation here. Wavelength, lambda, the de Broglie wavelength, equals h over mv. So this first one, the electron, the wavelength of an electron, is going to be h divided by the mass times the velocity. All right, and we calculate that out. And these are all reasonable numbers, so as far as these things go, and then we'll talk about what that means. Oops, 9 point. 1, 1. And so I get, doesn't really get it. Does anybody's calculator do a better job on this? Maybe we have a fancier calculator. Can't handle all the decimal places. So anyway, it's about 7 times 10 to the minus. What do you get? 7.2. Okay, and that's in meters. So you're talking about now less than a nanometer. You're talking about 70 picometers, right, or 0.07 nanometers, which is actually, it's small, but it's a reasonable wavelength. Right, it's still, and so in fact we use electrons to do spectroscopy, and we're going to talk about next how we can look at the wave nature of electrons. Okay, now let's compare that with the ball. So same equation, but we're going to substitute these masses for the ball, which I have here actually. And that comes out to 1.89 times 10 to the minus 34 meters. So incredibly, incredibly small wavelength. I mean, 10 to the minus 34 compared to 10 to the minus 11th is like almost immeasurably small. And what that means is the wave nature of a large particle like a ball is basically insignificant. It doesn't matter. The wavelength is so short that the wave-like behaviors of a ball are, of a ball traveling relatively slowly, are insignificant because they're so far away from the wavelengths of anything that we would consider light or electromagnetic radiation. But the wavelength of an electron is actually important. And this, and I'll show you what this means right now. So first, to talk about this, we have to talk about diffraction of light. I'm going to try to zoom this in a little bit so you can see it. So I don't know if you guys have seen this in physics or what, but when waves or particles encounter a very small hole or a slit, they behave in two very different ways. Let's look at the particle one first, because that's what we know. If you take a bunch of bullets or something and you shoot them at a thing with a little hole in it, some of them are going to go through and some of them are going to get stopped. Right? That's pretty straightforward. If waves going like this encounter a slit, and that slit is approximately the same size as the waves themselves, they do this weird thing called diffraction, where they kind of bend and change the direction that they're going. So if they're going this way, they're going to kind of start going this way and this way when they encounter that slit. And that's known as diffraction. So we usually say, well, particles don't really diffract. They just either get stopped or don't. But waves get diffracted. They get bent by these slits. And then when you have two slits, you get some interesting patterns. So you have a light source. Let's start over on the left, and I'll move to the right. You have a light source that's making these light waves go forward in different ways. They encounter these two slits, and they both get diffracted. So now you've got waves kind of going in various directions. And what's actually going to happen is they will either constructively or destructively interfere with each other. So when the waves happen to be out of phase after they've diffracted, you get a dark spot because the two parts of the wave cancel out and you end up with 0. If the waves are in phase, you get a bright spot, and then you sort of get the things in between. So when you shine a light at a diffraction grating with basically spacing or splits that are approximately the size of the wavelength of the light, then you get this diffraction, and if you put film in front of that, you'll get alternating dark and light spots all the way through the film. So you would imagine with particles, you wouldn't get that. You would just get two bright spots where the particles went through, rather than this kind of weird interference pattern. This is what happens from diffraction. So the reason I tell you this is that there's a really interesting experiment that deals with this with electrons. So when you actually, when you shoot a beam of electrons through slits that are very close together, you get an interference pattern when you measure the electrons on the other side. So even though electrons are particles, you don't get this. This is what you would expect. You got a bunch of particles, you shoot them at some slits, some of them pass through and make two bright spots on the electron film. Everything else is dark. But instead, what you actually get is a diffraction pattern, which means that the electrons are acting like waves, not like particles. But here's where it gets really crazy. If you take a laser beam and put it in front and try to detect where the electrons are coming out, so you can see whether they're coming out in one place or another, then suddenly your diffraction pattern changes. So just the act of measuring it changes the behavior of the electrons from a wave behavior to a particle behavior. And this gives rise to what we consider the Heisenberg, or what we know as the Heisenberg's uncertainty principle, meaning that the more precisely you know where something is, the more uncertain you must be about the velocity, and vice versa. So if you know where something is, you don't know what direction it's going in or how fast it's traveling. If you know what direction something's going or how fast it's traveling, you don't know where it is. And it's kind of a crazy thing. And that's why a lot of the quantum mechanics stuff was completely rejected when it was first being developed, is people just couldn't believe that this was actually happening. I mean, we're used to measuring something to find out something about nature of reality, and here they're telling us, well, as soon as you measure it, you actually change it. And so as soon as you observe something, just the act of observing it changes it, even though you're not like touching it or doing anything to it. So a lot of this is very kind of strange. However, the math behind it and the theory behind it do actually work. So eventually people couldn't really discount it anymore because it worked. They could show that it predicted all this stuff that the previous models, the classical mechanics, failed at. And so ultimately this became the true thing. Okay, so that's kind of the crash course in the beginnings of quantum mechanics. Now let's talk about some more concrete stuff and some of the stuff that we're going to be doing in lab on Monday. Do we need to take a break, or was our fire drill our break? It doesn't matter to me. I mean, do you want to take some minutes? Okay, because everybody seems like they're kind of falling asleep. So here's another place where classical mechanics breaks down. All right, meaning that when you're actually trying this, for a long time people couldn't really explain what was going on. Here's the thing. You could? Or you could? Yeah. So you excite a gas in a lamp. Right? You put gas in an evacuated tube, and you pass a high voltage across it, and it lights up. That's how we get fluorescent lights and neon signs and all that kind of stuff. That's been known for a really long time. But here's what's strange about it. You pass that through a prism. You pass that light through a prism, and it splits into different specific lines of light. So I don't know if you've seen prisms, but what was expected... Good.
I did not mean to do that.
What's expected when you put light through a prism is this bottom spectrum. You expect to see all the different kinds of light kind of spread across the spectrum. You're just kind of spreading it out. If you go like out in the sun and you put a prism up against a screen or something, you see something like this, although not exactly. But that's white light. That's all the wavelengths of light. But if you take any element and you excite it so that it gives off light, it doesn't give off this light, even though based on all the early predictions it was supposed to. So in fact, you need quantum mechanics to predict what actually happens, which is that you get individual lines, and it's different depending on the atom, depending on the element. So hydrogen leads to one set of lines, helium leads to a different set of lines, barium leads to a different set of lines, and so on. And you're going to see this on Monday when we burn different things and look at the light that they give off. So that's known as the line spectrum. And the only way that it could really be explained at the time is something called the Bohr model of the atom. So what he said was that you have these electrons that occupy different shells, going from the closest to the nucleus, the n=1 shell, and then increasing in number out to the outer shells. And then what happens when you excite these things is you have an electron that travels from an outer shell to an inner shell. Outer shells are higher energy, right? Higher potential energy. Inner shells are lower potential energy. So when an electron travels from a higher shell to a lower shell, it gives off energy in the form of light. And in that way, that energy that's given off is quantized. So if an if an electron starts at this level, it can only go to these few different levels. And in doing so, it releases light. So what he said was, okay, well, first of all, hydrogen only has one electron, right? So that's at the n=1 shell, the very lowest one. So you put the energy in with the voltage, it excites the electron out to these outer shells. And then the electron is allowed to fall down to the inner shell, give off light. So what he said is like, okay, if an electron goes from an n=5 shell to an n=1 or n=2 shell, that gives off violet light of 434 nanometers. If it goes from n=4 to n=2, that gives off light of 486 nanometers. And remember that we had this equation from Planck and Einstein telling us what the energy of a given particle, of a given photon is with a certain wavelength. So you could say if that's the amount of energy between these two shells, then we know what kind of light is going to come out. And by the way, this isn't entirely true. Now we know that it's a little bit more complicated than this. But it worked well at the time, and it certainly worked better than what was before. And this was the first quantum model of an atom. And so what he found, just by doing these measurements and looking at these different light lines, was that you could express the energy levels as this constant times z squared, which is the nuclear charge or the atomic number, divided by n squared, which is the integer. So n=1 was that first shell, and in this way we could calculate the energy of the first shell. n=2, the next shell. n=3, the next shell, and so on. And then he said, all right, we can figure out the energy change when an electron goes from one shell to another by subtracting these two calculations. We can take a final state, calculate that energy, and an initial state, calculate that energy, and then we can figure out what wavelength photon might come out. So that allows us to do problems like this. Calculate the energy required to excite the hydrogen electron from n=1 to n=2. Also, calculate the wavelength of light that must be absorbed by the hydrogen atom in its ground state to reach this excited state. So ground state is like the normal stable state. Excited state is when the electrons are excited into higher levels. All right, so let's try this. What we're going to do is go back up here and look at this equation. E equals that number times z squared over n squared. We'll talk about what that constant is shortly if we get there. But let's try this first. E equals 2.178 times 10 to the minus 18 joules times z squared over n squared. So for the energy of shell number 1, it's going to be that constant times, well, okay, let's talk about that number for a second. We'll just call that C for now, for a constant. That's this number. Okay, what's z squared going to be? What's z going to be? Remember, z is the atomic number, so z for hydrogen is going to be 1. And what's n squared going to be? Well, n in this case is just the shell. So if we're looking for the energy of the n equals 1 shell, of an electron in the n equals 1 shell, that means n squared is going to be 1. So 1 squared over 1 squared is 1, and that equals c. So the energy of the ground state first level of hydrogen is this much. That's how much energy an electron has in the n equals 1 shell of hydrogen, according to the Bohr model. And we can do the same thing for the energy in the n equals 2 shell. Still 1 squared here, but now we're 2 squared down here. So that's going to be c times 1/4, which is about, wait a second, I missed some negatives here. This should be negative, 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 negative. Sorry, that's all negative energies. So that becomes negative 5.445 times 10 to the minus 19th joules. Okay. So a smaller number. Less negative. All right, and then we can figure out the difference in energy by subtracting those. So the change in energy, which is what's required to excite the electron from one to the other, is the difference in those two levels. So let me describe that for a second. These is there a picture here? Let's look at a picture. I guess I don't have a picture in these notes. We're going to do it later. C is just this constant because I didn't want to write that number a bunch more times. Okay, back to where we were then. The change in energy is the difference between these two levels. And that's going to be E2 minus E1 because it went from E1 to E2. That's what it was excited as. And the equation tells us that the change is the final state minus the initial state. So we subtract those two numbers. That's this number minus this number. And you end up with 1.63 times 10 to the minus 18th joules. So that's the amount of energy you need to put into a hydrogen atom to excite an electron from the ground state, the n equals 1 shell, to the excited state. Okay. Second part of that question is, what is the wavelength of light that must be absorbed to do this? So if you want to transfer this electron by putting a photon into it, by shooting a photon at it, what does the energy of that photon have to be? And the answer is that we use this equation from before, Planck's equation, E equals hc over lambda. So that's going to be those two constants, h and c. Whoops. So this is going to be this energy. Let me just redo that. 1.63 times 10 to the minus 18th joules equals hc over lambda. H and c are constants, right? We can look those up, plug those in. Solve for lambda. We get lambda equals hc over 1.63 times 10 to the minus 18th. And that comes up to 1.21 times 10 to the 7th meters, or 121 nanometers. So light of 121 nanometers, which is ultraviolet light, will excite an electron from the n equals 1 shell of hydrogen to the n equals 2 shell of hydrogen. Good so far? Maybe? All right, we're going to do this more. Okay. You can actually combine those equations together, so you don't always have to calculate each individual level to get the change in levels, the change in energy. And usually we care more about the change in energy than we do about the energy levels themselves, because the change in energy is what gives us the light in the spectrum, or is what the light is we need to put in. So by combining the equations from before and doing a little bit of algebra, you come up with this. A general equation to calculate the energy, or the change in energy, between any two levels is the same constant times 1, let me rewrite this in case it's not clear. This is 1 over n final squared minus 1 over n initial squared. Okay. Sometimes it's hard to put those things into the notes. I've got to use the equation editor. NF, the final level, is where the electron ends up. Ni, the initial level, is where it starts. So that allows us to do what we just did, but a little bit easier. Let's go, before we do this next problem with it, which is a little bit trickier, let's go back to what we did here. So let's say we had this question again, but now with this new equation. Calculate the energy required to excite the hydrogen electron from n equals 1 to n equals 2. What we did was we calculated the individual potential energies for level 1 and level 2, and then we subtracted them. What we could have done, now that we know this, is simply use this equation with NF equals 2 and NI equals 1. And then we would get the same thing. All right. So that said, how do we figure out a problem like this, which is a little bit trickier? The energy required to remove the electron from a hydrogen atom in its ground state. What does it mean to remove the electron in terms of exciting to different energy levels?
How much energy is required to put in?
Yeah, how much energy? But how are we going to use this equation, right? We've got NF and NI. NI is going to be 1 because that's the ground, the regular ground state. But what's NF if we want to remove the electron? What does that mean? Infinity, right? Yeah. As NF goes to infinity, then what happens to the equation is what it's really saying. What does it calculate? So NF gets very, very large as you excite higher and higher. So the ground state tells us that Ni equals 1. Remove the electron tells us that NF equals infinity. So what does that mean mathematically? It means we're looking at a limit problem. So what happens to this equation? What happens to minus 2.178 times 10 to the minus 18th So what happens to this equation as NF goes to infinity? What becomes 0? No, NF becomes infinity. What happens to the equation?
It gets smaller and smaller and smaller.
Yeah, so as this goes to 0, or I'm sorry, as NF goes to 0, this gets small because it's on the bottom. So as the bottom NF gets super, super big, that whole term kind of tends towards 0. So this whole thing then, as NF goes to infinity, this quantity 1 over NF squared minus 1 over NI squared becomes 0 minus 1 over NI squared, or just negative 1 over NI squared. All right. So that means that this equation becomes negative 2.1, nothing changes with this number, times 1 over Ni squared. Ni is 1 because we're starting in the ground state. So it's just going to be 2.178 times 10 to the negative 18th joules. So that's how much energy is required to remove an electron from a hydrogen atom in its ground state. Okay. All right, now I told you a little bit earlier that this wasn't quite right. It's not quite right. Has two pretty major drawbacks, unfortunately. Did somebody just go, oh, yeah. So this was a great accomplishment for Bohr because it predicted this hydrogen spectrum that had been baffling people for a long time. Why does it make these lines? It makes the lines. Now Bohr says it makes the lines because the electrons are in these orbits and they change levels of the orbits, and so we see these differences in energies. And everybody said, hooray, you're brilliant, good job. But your model fails on two pretty big accounts. Number one, it only works for hydrogen. So that's a little bit limiting. It doesn't accurately, it gets close on some of the other elements, but it doesn't accurately predict the spectra for those other elements. And the reason for that is that it can't account for more than one electron. Right? Which we see. The equation tells you what happens when an electron moves from one shell to the other. But what happens if 3 electrons are moving from one shell to 3 different ones, and then they're falling down into some other ones? What happens if 4 or 5 or more? You know, that equation has no way of working with that. So we have to get much, much, much more complicated. And then there's another issue that is still a huge problem today, and that is that we can't exactly solve for what happens when multiple electrons repel each other. That's a very complex process, and when you have multiple electrons, it actually changes the energy calculation and makes it much more complicated. So the top quantum mechanical calculation experts today have actually stopped really trying to solve that, and we just approximate it with computing power, like trying every possible combination of changing things slightly, and that's kind of how we approach that question. All right, so let's get into the quantum mechanical model here. We're not going to do these calculations, but what was sort of the way to not solve this, but the more modern way of thinking about this is that the wave of an electron are these kind of standing waves with increasing number of wavelengths and nodes as you go away from the nucleus. And this is what's now known, or what we call orbitals now. So we're going to talk somewhat a bit about some of that. What figure am I looking for here? I don't think that figure number is right. This must be from the previous edition. I'm sorry about that. I'll let you know when I find it. Anyway, don't worry too much about this stuff. We don't have too much time left anyway. But this thing, psi, is called a wave function. And the wave function represents how the electron is moving in space, right, in the Cartesian or polar coordinates. And this type of equation, what this is saying, H psi equals E psi, is an important equation by this guy Schrödinger, who's kind of the father of modern quantum mechanics. And H is called an operator. And an operator is a mathematical thing that you do. So part of the Hamiltonian operator, which is that H, is like take a derivative and add this thing and multiply this thing. It's kind of a set of instructions on what to do to the function next to it. And what this is solutions for this equation, meaning a wave function or a mathematical function that when you do these things to it, you get back the same function again times a constant, which is E. All right? That's known as an eigenfunction, and the E is known as an eigenvalue. Just means do these things to this function, you get the function back times some constants. All right. And so these constants actually have to do with the energy levels. These E, that's why it's E. We can actually measure some of the energies based on those. And the different solutions for this wave equation are things called orbitals, which describe how electrons move in an atom. All right? And that's kind of what we're getting at here. So this term orbital is kind of a tribute to Bohr, because an orbit is something going around and around something else, right? Like a planetary orbit. And that's what Bohr thought was going on with electrons. When they found out that wasn't actually true, they said, well, electrons are actually behaving in this much more complicated way, but we're going to give them credit and call it an orbital. So it's kind of orbit-like, but it's not exactly an orbit. All right, so it's kind of like being nice to him. All right. Tribute. Okay. So the physical meaning of a wave function is a probability density or a distribution. We remember from the Heisenberg uncertainty principle, we can't know the position and the velocity. So we can't know the exact path that an electron takes in an atom. That's one of the reasons the orbital is certainly wrong. We can't know exactly how it goes. All we can know is where could it be in a probability. So here's the difference between a classical trajectory and a probability distribution. If you throw a ball on the left, right, you can calculate the trajectory that the ball follows this exact path and goes from here, passes through all these positions, and ends up over here. That's a trajectory. Okay? In quantum mechanics, we don't have trajectories because we can't figure out exactly where the particle is. So instead, we have a probability distribution. We say, at any given time, the electron could be somewhere within this thing, within this arc. We don't know exactly where. We don't know how fast it's moving. Or if we do know exactly where, we don't know how it's moving, so we can't give it a direction. And if we know how it's moving, we don't know where it is, because uncertainty principle. So you have this kind of, I don't know if you can see that from the screen, but it's sort of a bunch of little dots. There's a greater probability that the electron or the particle is in the middle of that line. And then as you get off, the probability starts to drop to 0 as you get further away from that line. And that's exactly how we think about orbital. The difference between an orbit and an orbital. An orbit is the thing on the left, and that's not right because we don't know how the electron is going. An orbital is the thing on the right. We know sort of where the electron is most likely going to sort of be, or a collection of places that the electron will most likely be. And this predicts that actually pretty well. So here is what a 1s orbital looks like. This is the smallest orbital in the atom, the one closest to the nucleus, what Bohr might have called the n=1 shell. We're now going to say is an electron in the 1s orbital. And the 1s orbital actually is a probability distribution that looks like this thing on the left. The denser, the more dots there are, the higher the probability that the electron is there. And the probability kind of falls off as you get outer, as you get further and further out. We don't know exactly where the electron is in there, and it's not moving around in there through a specific trajectory. It's just sort of probably there, right? And then when we do stuff with these orbitals, when we talk about how they bond and how they interact, we think about the orbital surface. So what you may have seen in your previous chemistry classes is that an s orbital is a sphere. Well, that's true, but it's really just the surface of the probability density that's a sphere, or approximately a sphere. Okay. And so we use that. We use this definition. The radius of a sphere that encloses 90% of the total electron probability is the size of the atom. That's how big the atom is. So let's see if we can get through these quantum numbers, and then we'll call it a night. Now, remember we talked about these functions that solve this Schrodinger equation. You do this operator to them, and you get the function back with these various energy values. Well, these functions, these are sort of somewhat parametric equations, which means that they can have these various parameters, these various numbers. And depending on which number they have, they get solved in a slightly different way. And we're not going to get into all of that. But what is important is to look at the numbers that actually describe these equations. And these are known as quantum numbers. And they help us describe what the energy of an electron is and what orbital it's in and sort of where it is. So we've got 3 quantum numbers now, and we're going to learn one more later. Principal quantum number is related to the size and the energy of the orbital. This is kind of like Bohr's quantum numbers. N equals, but it starts actually at 1, kind of also like Bohr. And it tells you that the orbital is either in the shell number 1, shell number 2, shell number 3, shell number 4, as you get out. Now, unlike Bohr, we know it's not actually a shell or a trajectory or an orbit. It's this sort of probability density that gets bigger and bigger. But this actually correlates to the periodic table. The outermost shells of the electrons, the n equals 1 is the first period across. The outermost electrons are in the n equals 2 shell for the second period, n equals 3 for the third, and so on. All right? Then you've got the angular momentum quantum number, which is known as L. This tells you how it's angular momentum because of the way that the electron is moving, but importantly to you, it tells you what type of orbital you have. If you have a certain n, you can have L's from 0 to n minus 1. So if you are in the n equals 3 shell, the electron can have a quantum number of L of either 0, 1, or 2. And this has to do with what type of an orbital it is, which you may have heard before. An s orbital, a p orbital, a d orbital, an f orbital. Those are assigned to those numbers. L equals 0 is an s orbital, 1 is a p, 2 is a d, 3 is an f. And we'll talk about those shapes and what that means a little bit later. We can also sometimes call these subshells. So they're inside. You talk about a 1s orbital. An electron in a 1s orbital has a quantum number n equals 1 and a quantum number L equals 0. An electron in a 2s orbital has a quantum number n of 2 and a quantum number L of 0. So any s orbital will always have an L quantum number 0. Any p orbital has an L quantum number 1, etc. All right? And then the magnetic quantum numbers go from L to -1. So if L equals 1, that is a p orbital, ML can either be -1, 0, or 1. This tells you that there are 3 different p orbitals that are oriented in space in different ways. So let's break this down for an example of quantum number n equals 5. So in quantum number n equals 5, how many subshells can you have? How many different values of L can you have based on the rules there? Well, you can have 5, but they go from 0 to 4. Okay? So if n equals 5, then L can either be 0, 1, 2, 3, and 4. Okay. And we can name these. 0 is known as an s orbital, 1 is known as a p, 2 a d, 3 an f, and 4 a g. Which means the n equals 5 shell contains s orbitals, p orbitals, d orbitals, f orbitals, and g orbitals. And then we can break this down in terms of the MLs also. So an s orbital can only have ML equal 0 because it's L to -L. That means there's only one kind of s orbital. All right, only one orientation. It's a sphere. A p orbital can have ML equal -1, 0, and 1. Again, L to -L. So there are 3 different p orbitals. A d orbital is 2, so it can go from 2 all the way to -2 which means that there are 5 different d orbitals.
How do you know this stuff?
Because of these definitions. ML has integer values between L and negative L. So if you go between L and negative L, you get 5 different spots. And that tells you how many orbitals are there. Okay. And then for F, you now have 7, because you can go from -3 all the way to 3. And G, you have 9, going from -4 all the way to +4. So there are 5 subshells and this many, whatever that is, orbitals in the n = 5 shell. All right, another question. Why is there no 1p orbital? Why isn't there a p orbital in n = 1 shell? Yeah, it doesn't get that far. Right? You can only have values of L from 0 to n-1. So in the one shell, n-1 equals 0. So the only value of L can be 0, which means you can only have an s orbital in the n = 1 shell. Now let's put a picture to these, and then I think we'll be done. Actually, we pretty much are done. Yeah, that is pretty much the end. So, okay, let's put some pictures to these things. Point of all this is, if you take a wave function that has these values for quantum numbers, that has these n, L, and ml that you can plug into this equation, and you square it, you get a probability density that looks like this. So if you plug in n = 1, L = 0, you get this probability density, which we talked about before. It's basically spherical, and as you move away, as you travel along R, move out on the radius from the center, the probability density drops off to 0. If we go out to the 2s and 3s orbitals, things change a little bit. I'm going to zoom in on this so you can see it better. Here's a 2s orbital. That means n = 2 and L = 0. It also basically looks like a sphere on the outside, but on the inside it actually goes through what's called a node. And a node is an area of 0 electron probability. So that means that an electron can never be in that spot. All right? Which is interesting because it can be on either side of it, but it can't actually be in it. So it travels without actually, it is on one side and then on another side without actually going through that because it can't be there. So, what? Yeah, it's pretty weird. Yeah, it's called, or it's related to something called tunneling, but it's basically weird. I mean, the math works out and you can predict it, but it's still sort of weird. You can't really. So here's the probability density, which means as you go toward the center, it gets infinitely probable, but then you go through this node, then it gets more probable again, and then it drops off to 0. And then here's something called the total radial probability, which accounts for the fact that the nucleus is actually in the middle. So even though the wave function, the solution for the wave function shows that the probability should increase as you go toward the middle, towards 0 from the nucleus is actually there, so we know it can't be at 0. So if you account for that, this is really what it looks like. There's a slight area of probability just outside the nucleus, and then most of it further outside the nucleus. We go to the n = 3 shell, and we see a much larger s orbital with now 2 nodes. So again, here's the radial probability. And most of the electron density is located outside, or most of the electron probability is located further out. So what this means is, or what this means for us, is that as electrons fill higher shells from 2 to 3 to 4 to 5, the atom gets bigger because the electron is spending more of its time, or there's more probability of it further away from the nucleus. That's what these graphs are telling you. that these orbitals are bigger from a radial surface standpoint than the n equals 1 or n equals 2. And then we can also look at p orbitals. So remember a p orbital, is when L equals 1. And if L equals 1, then ML equals -1, 0, or 1, which means there are 3 different types of p orbitals. They all kind of look the same, but they're oriented in different ways. And they all have nodes also, which are areas of 0 probability. There's one oriented along the x-axis, known as px, one along the y, known as py, and one along the z, known as pz. Now you can't know, based on quantum numbers, which one is which. All right? So we know L equals 1 is a p orbital, but we don't know that ML -1 is one of those, or ML 0 is one of those. There's no way of knowing that. So those ML numbers don't correspond to specific orbitals like these. And then the d orbitals get fancier, and the f orbitals fancier still. So you can see now the 5 different d orbitals, the 5 different orbitals with L equals 2, they don't just change their orientation, they can actually totally change their shape, as in this dz squared orbital, which is like a donut with a p orbital type thing in the middle of it. Again, this all comes from solving these equations with these numbers. And then we also talk about the phases of an orbital. We didn't see this above in the shapes, but a 1s orbital is all the same phase. A 2p orbital has 2 different phases. And that becomes important with bonding, because to form a chemical bond or a covalent bond, the phases actually need to line up. So we're going to talk about what that means and how we see that. All right. I think that's it. So hopefully that was pleasant.